Today we're going to cover Module 9 out of your textbook. It's Weld and Base Metal Discontinuities. We got some videotape to watch as well, but I'm going to start on page 9-2. We're going to cover a couple of pages here, and then we're going to turn and watch some training videos and do some things, and then we'll come back to the text a little bit later. I want to start on page 9-2, and you can look at our slides here. Module 9, Weld and Base Metal Discontinuities. What's a discontinuity? Well, by now you should understand what a discontinuity is. Any interruption in the uniform nature of an item. Find that description in your text and highlight it. That will be a bullet. It's in the second paragraph in the first column, and it says, in general, a discontinuity is described as any interruption in the uniform nature of an item. Staying in that same paragraph, drop down to the last sentence and highlight where it reads, in welding, the types of discontinuities with which we are concerned are such things as cracks, porosity, undercut, incomplete fusion, etc. So these are all the things that we're going to be talking about. These first two are manufacturing defects, seams and laps and laminations. Those occur at the plant, at the mill where they're making the base metal. These others are things that happen from poor welding technique or trash in the welds, and we'll discuss all of those. Stay in the first column, drop down to the last sentence and highlight where it says, as a welding inspector, you should strive to realize the distinction between the terms discontinuity and defect. What is a defect? A non-conforming discontinuity. And it says, this is the distinction. All discontinuities are not defects. All defects are discontinuities. So let me draw that on the board real quickly. Real simple explanation. If we have a block of steel, and in this block of steel we have a void, that void is an interruption in the uniform nature of that block of steel. So therefore, by definition, it is a discontinuity. Now, if that discontinuity is measured against some code or standard, and we find that it is less than or equal to 1/8 of an inch or 3.4 millimeters, it may be acceptable. If, however, it is greater than 1/8 of an inch or 3.4 millimeters, then it becomes a defect. So it's all dependent on the size of the discontinuity. Therefore, all defects will be interruptions in the uniform nature of the material, but if they don't reach that size, then they remain discontinuities. So they're all, any interruption is a discontinuity, but it's got to be the correct size before it becomes a defect. So that is our distinction. And if you look in the second column, top paragraph, it will explain that. It says, while a discontinuity is some feature which introduces an irregularity in an otherwise uniform structure, a defect is a specific discontinuity which can impair the suitability of that structure for its intended purpose. That is, a defect is a discontinuity of a certain type and one which occurs in an amount great enough to render the particular object or structure unsuitable for its intended service based on criteria in the applicable code. So if it's too big a defect or too big a discontinuity that it's going to impair the ability of the weldment to serve its intended function, then it becomes a defect. It's not acceptable. Staying in the second column, drop down to the last paragraph and highlight that where it talks about the criticality of discontinuities. They rank them in different orders of magnitude. You have linear, that is a straight line discontinuity. Well, they're more severe than a rounded discontinuity. So linear, you have linear discontinuities and nonlinear discontinuities. The end condition of the discontinuity is very important, and when they talk about the end condition, they're talking about the sharpness. And then also something else that affects it is on the surface or is it below the surface of the weldment? And then how is it loaded? How is the discontinuity affected by loading? Is it uniform loading or is it non-uniform loading? Is it fatigue loaded or is it impact loaded? All of these things help to help us to identify how critical the discontinuity is. So highlight that last paragraph in column 2 where it reads, "We can, however, talk in general about the effect of criticality of certain discontinuities. Such a discussion will help you understand why certain discontinuities are unacceptable, regardless of their size or extent, while the presence of minor amounts of other discontinuities are considered to be acceptable." Then go over to the next page, 9.3. Now I've highlighted just about the entire first column over here. Put a bullet by the top where it says, "One way in which this can be explained relates to the specific configuration of that discontinuity. Configurations of discontinuities can be separated into two general groups, linear and nonlinear. Linear discontinuities exhibit lengths which are much greater than their widths. Nonlinear discontinuities, on the other hand, have length and width dimensions which are essentially the same. When present in a direction perpendicular to the applied stress, a linear discontinuity usually represents a far more critical situation than does a nonlinear type because it is more likely to propagate and cause a failure." So if we've got a weld, say a fillet weld, and we have a crack running down the middle, that's going to be a much more severe discontinuity than some porosity, especially if it's subsurface porosity. Because these are rounded indications, they're not likely to propagate, but this is a linear indication, which if we put this weldment under vibratory stresses, that repeated cyclic pounding on that will make that crack grow until ultimately it will fail. So that's probably the number one criticality consideration is its in condition, and whether it's linear or nonlinear. And if you look in your codes, it's reflected in that. Most codes allow no cracks at all. In fact, I don't know of a single code that allows any of it. But porosity, on the other hand, most codes do allow certain amounts of porosity because they're not as critical. Second column, second paragraph, it talks about end condition. And reading from the second sentence, it says, "By end condition, we are referring to its specific sharpness at its extremities. In general, the sharper the end of the discontinuity, the more critical it becomes." Again, drop down to the next paragraph. It's a bullet. "If we were to rate some of the more common discontinuities with respect to the sharpness of their end condition, starting with the sharpest, we would generally have crack, incomplete fusion, incomplete joint penetration, slag inclusion, and porosity." So we have a descending order of criticality based on its end condition. This order coincides with the amounts of these discontinuities permitted by most codes. There are only a few instances in which any amount of cracking is allowed. Incomplete fusion may also be forbidden, or at least limited to minor amounts. Most codes will permit the presence of small amounts of incomplete joint penetration and slag, and some porosity. Depending on the industry and the intended service, these amounts will vary, but in general, the sharper the discontinuity, the more its presence is restricted. Okay. Go ahead and move over to the next column now. Second paragraph. I've highlighted that entire second paragraph where it reads, "A final way in which the criticality of a discontinuity is judged relates to the way in which the part or structure will be loaded during service. For example, if a weld forms part of a pressure boundary, those weld discontinuities constituting a significantly large percentage of the wall thickness will usually be most damaging." Take porosity, for example. If you've got a bubble of cluster porosity in the center of a weld, say on 6-inch Schedule 80 pipe, well, that wall thickness is only 0.432 inches thick, so less than a half of an inch. And if you've got porosity all through there, you've removed an awful lot of the weld metal in that particular little area. So it's not going to have the pressure retaining standard that you would want with that. And so we've reduced that wall thickness and it's more likely to fail. So it says, in the case of a structure which will be loaded in fatigue, and that is cyclic loaded, I've underlined this part, those discontinuities forming sharp notches on the surface of the structure will generally cause failure more readily than those beneath the surface. And when they're talking about sharp notches, we're talking specifically about undercut, but that category also includes improper weld contour on the cap, for example, or overlap. Those are all stress risers. Anything thing that disrupts the geometry of the surface of the weldment is going to be more critical than a little bit of porosity underneath the weldment. They're just stress risers, and it can lead to failure a lot more rapidly than subsurface. So these surface notches act as stress risers, which tend to concentrate or amplify the stresses at that notch point. Such a stress concentration can result in a localized overload condition. Even though the stress applied to the full cross-section may be low, stress risers can amplify the applied stress by factors as high as 10 in the case of a sharp surface crack. So here we've covered the various, in detail, the various criteria that would determine how critical a discontinuity would be. Now, if you'll flip the page, you'll see in the first column on page 9.4, in the blue box, you'll see a list of discontinuities, beginning with crack, incomplete fusion, incomplete joint penetration inclusion, slag inclusion, tungsten inclusion, porosity, so on and so forth. It's presented in this blue box in the order that it's going to be talked about in this module. All right, page 9.4 in your textbook. We're going to go down, run through these all pretty quickly. Just highlight where I tell you and put a bullet by where I tell you. And first of all, we're going to start with a crack. Definition of a crack. Crack is a fracture-type discontinuity characterized by a sharp tip and high ratio of length and width to opening displacement. On page 9.4, go ahead and highlight the column right below that blue box and put a bullet by it so you know the definition of crack, and read over onto the second column, highlighting the remainder of the first paragraph up there. And then in the middle of the second column, we're going to read about hot cracks. So this is in the third paragraph. I'm reading. It's in italics now. Put a bullet by it, underline it, highlight it. Usually hot cracks occur as the metal solidifies at some elevated temperature. The propagation of these cracks is considered to be intergranular. That is, the crack occurs between individual grains. If we observe the fracture surfaces of a hot crack, we may see various tempers. That is, colors on the fracture faces indicating the presence of that crack at elevated temperatures. I believe they also refer to those as chevrons. Those little, they're kind of like waves. Then cold cracks. Bullet, underline it, highlight it. Cold cracks occur after the metal has cooled to ambient temperature. Those cracks resulting from surface conditions would be considered cold cracks. Delayed or underbead cracks resulting from entrapped hydrogen would also be categorized as cold cracks, and that's important. I believe that may be a question. Underbead cracking, hydrogen entrapment, cold cracks. The propagation of cold cracks can be either intergranular or transgranular, that is, either between or through the individual grains, respectively. So what that really means is when you got your weldment and your grains are like so. Of course, you have that grain matrix in here, and of course it solidifies from the cold wall towards the center. And hydrogen cracking, it happens when you have two atoms of hydrogen combining, and what happens is that they form a molecule. The molecule is too big to nestle in between the grains, and so it will crack along the grain boundary, or it can crack through the grain boundary. And that's what they're talking about. Last seminar I attended that talked about welding metallurgy. It's transgranular like this, that they consider to be the most common type of hydrogen underbead cracking. So delayed or underbead cracking caused by hydrogen entrapment, hydrogen molecules. They're too big to nestle in the grain matrix, therefore they exert pressure, and that leads to cracking. Put a bullet by longitudinal cracks. That's in the next paragraph. The same picture is on page 9.5, top of the page, and you can see we have a crack running right down the center of it here. And this would be considered a longitudinal crack. Next slide, transverse cracks. Here's an x-ray of it down here. This is a really nice picture. You can see how the cracks show up on x-ray, and here's the corresponding crack here and here. And of course, the way an X-ray works, the denser the material or the thicker material, the fewer X-rays travel through to the film. The X-rays that do travel through to the film darken the film, and so it's less dense in those areas, and that's why we can see the crack. There's nothing to inhibit the rays from passing through. So that picture is also on page 9.5. It's at the bottom of the first column. And reading from the, going to page 9.5 here, reading right under figure 9.1, it reads, transverse cracks are generally caused by the longitudinal shrinkage stresses of welding acting on welds or base metals of low ductility. So if it's a higher carbon, remember the more carbon we put into a metal, the stronger it is, the harder it is, but the less ductile it is. So if you have a high carbon material, it would be more susceptible to transverse types of cracks. Drop down to the next paragraph, highlight the last sentence and put a bullet by it. Says, these descriptions include throat, root, toe, crater, underbead, heat affected zone, and base metal cracks. So read that and put it into context. And then throat cracks, underline it, that's a bullet. Here's a picture of a throat crack. You have this in your textbook. It's figure 9.4, and it's running right down the center through the throat. If we were to draw a picture of that, when they were talking about a throat crack, not only do you see it exposed to the surface, but it's running down through here. And so it's running through the throat of the weld. Let me read that paragraph. It says, throat cracks are so named because they extend through the weld along the weld throat, or the shortest path through the weld's cross-section. These are longitudinal cracks and are generally considered to be hot cracks. A throat crack can be observed visually on the weld face. Consequently, the term centerline crack is often used to describe this condition. Over on the next page, underline and put a bullet by root cracks. Root cracks are usually longitudinal. However, their propagation may be either in the weld or base metal. Read about that. Then drop down to the bottom of that paragraph. Underline and put a bullet by toe cracks. Toe cracks are base metal cracks which propagate from the toes of the weld. And here's some example of toe cracks. I believe you have this in your book. No, I'm sorry, I guess you don't. You have something similar to that on the next page, though, 9.6. You do have this one in your book. I don't believe you have this one, but you have something similar. And you can see a toe crack here. It's where the weld metal is pulled away from the base metal. And here's a cross-sectional picture of one. Here's the toe on each side, and you can see that it propagates down into the heat-affected zone area. So those are toe cracks. Read about those. And then we have crater cracks. Now this is a crater crack, also known as a star crack, and this is on page 9.6 in your textbook. And it says crater cracks occur at the termination point of individual weld passes. Read about crater cracks and how they're formed. And then in the next column it says, since crater cracks occur during the solidification of molten puddle, they are considered to be hot cracks. So keep that in mind. That may be a question on your test. This is also in your book, and this is a crater crack that propagated all the way around this pipe. It's an aluminum weld, but they didn't do anything to fix that crater crack. Put this thing in service, and it's sitting there vibrating back and forth, and that caused the crack to go ahead and travel all the way around this thing until it connected itself, rendering it unfit for service. Next page, first column, under bead cracks now. Put a bullet by it, underline it. It says the next category of crack is the underbead crack. Although related to the welding operation, the underbead crack is located in the heat-affected zone instead of the weld metal. That's important to remember. As the name implies, it will characteristically lie directly adjacent to the weld fusion line in the heat-affected zone. When cross-sectioned, underbead cracks will often appear to run directly parallel to the fusion line of a weld bead. So here's the fusion line. It's kind of hard to see, but here's the fusion line of this particular picture, and you can see that it's just in the heat-affected zone, right in here. And then here we have another one. There was a weld made here, and you can see the contour, and here's the crack right underneath there. And I believe Now, I believe you have both of these pictures in your text. So you can see it's just adjacent to the weld. And it says, underbead cracking is a particularly detrimental type of crack because it may not propagate until many hours after welding has been completed. For this reason, underbead cracks are sometimes referred to as delayed cracks. So that's a bullet. Consequently, for those materials which are more susceptible to this type of cracking, final inspection should not be performed until 48 to 72 hours after the weld has cooled to ambient temperature. Okay, so read about underbead cracks, and over in the next column, again, underline underbead cracks and highlight the next two paragraphs and read about them. And then you're going to read about the highlights. They're often delayed cracking. They're caused by hydrogen, just like I drew on the board. It's where the hydrogen atoms combine to form hydrogen molecules. They're difficult to detect. And how do you stop them? You try to avoid hydrogen cracking by reducing the sources of hydrogen. You want to reduce the sources as much as you can. So you're going to use a low hydrogen electrode. You're going to make sure that the weld environment is clean. You're going to make sure that there's no grease on your gloves. Anything that might be a source of hydrogen that could be sucked into the liquid molten puddle, you want to try to eliminate and keep it under control. And as the inspector, you should know what materials are more susceptible to underbead cracking than the others. Mild carbon steel, that's not so acceptable, but your book describes ASTM A514 example as a steel that is susceptible to delayed cracking. So you want to watch out for that and know the material. Staying in the second column, drop down to the next to last paragraph and highlight it. It says, since the heat affected zone is typically less ductile than the surrounding weld and base metal, it becomes hardened during the welding process. Cracking may also occur there without the presence of hydrogen. In situations of high restraint, shrinkage stresses may be sufficient to result in heat-affected zone cracking, especially in the case of brittle materials such as cast iron. A particular type of heat-affected zone crack, which has already been discussed, is the toe crack. Back in the film, they were talking about one way you could eliminate warpage and distortion was to restrain with clamps or some other means the weldment. Well, you have to keep in mind that distortion will relieve stress by allowing material to bow up. And so warpage will actually, warpage and distortion will actually relieve that stressing. So if you're going to clamp it in place, there's no place for that stress to go. So you've got to do something to relieve that. And then that something would be some kind of stress relieving process such as vibratory or heat stress relieving, something like that. Next paragraph is a bullet. Cracking may also be present in the base metal itself. These types of cracks may or may not be associated with the weld. Quite often, base metal cracks are associated with stress risers, which result in cracking once the part has been placed in service. Okay. Now, incomplete fusion. This will be our next topic. That's a bullet and highlight it. What is incomplete fusion? A weld discontinuity in which fusion did not occur between weld metal and fusion faces or adjoining weld beads. You have this picture in your text, and it's just an example of voids. Here we have a single V-groove weld, and here they didn't fill it in, here they didn't fill it in. Here along the fusion face, they didn't fill it in. Over here again, this would be a single bevel. The fusion face wasn't melted, and here they didn't tie in properly, and here they didn't break down the toe. Those are all examples of incomplete fusion. Incomplete fusion at the weld face. You have this picture in your book as well. On page 9-8, second column, last paragraph, highlight it, put a bullet by it. It says, another non-standard term for incomplete fusion is cold lap. This term is often and incorrectly used to describe incomplete fusion between the weld and base metal or between individual weld beads, especially when using the gas metal arc welding process. So know what cold lap means. It's a non-standard term for incomplete fusion. Incomplete fusion between weld metal and base metal, and you should have this in your book. You can see that it runs down here, and these sides are not melted down. It's not melted into the fusion face, and therefore it's just hanging down there. On page 9.9, put a bullet by the second paragraph. It says incomplete fusion can result from a number of conditions or problems. Probably the most common cause of this discontinuity is the improper manipulation of the welding electrode by the welder. And I've underlined that in my book because it's the most common cause. Poor welder technique. Finish reading the rest of that paragraph to put it in context, and then flip the page. A little bit later on, we're going to talk about this would not be considered incomplete fusion if the engineer decided that he only wanted a partial, if it's a partial penetration joint, then this would be pretty much irrelevant. But we're going to come back to that in just a minute. Now, this is an X-ray of sidewall incomplete fusion, and you can see how nice and straight it is. And so, remember, it's difficult to pick up incomplete fusion unless the source that you're using to take the X-ray is oriented properly to the fusion itself. Then it brings us to incomplete joint penetration. Incomplete joint penetration is defined as weld metal that does not extend entirely through the joint thickness. The term is used only for groove welds. So we're on page 910 now. Under incomplete joint penetration, but I've gotten ahead of myself. Back up just a bit. In column 1, go to the second paragraph where it says incomplete fusion is very difficult to detect with radiography unless the angle of radiation is oriented properly. That's a bullet. I briefly mentioned that, but I didn't really go into depth there. So highlight that, highlight the next paragraph as well. And then we're finally back online here where it says incomplete joint penetration. Understand the definition of that. And here are some examples of incomplete joint penetration. You have this slide on your next page. And incomplete joint penetration in a single V groove, a double V groove where they haven't completely fused it, a single V groove again where they didn't go all the way through, and then here at the root on this double bevel they haven't gone all the way through. Those are all examples of incomplete joint penetration. And in the second column on page 910, go to the middle of that first paragraph and put a bullet by it and highlight it where it says most codes place limits on the amount and degree of incomplete joint penetration permissible, and several codes do not accept any incomplete joint penetration. Then read the next paragraph. Now, incomplete joint penetration is not incomplete joint penetration if the engineer doesn't require it to be, and these are called partial joint penetration welds. So it's penetration not required to be complete by the designer. So highlight that and know that sometimes they engineer it that way. And I put a bullet by it and highlighted it where it says they could be called partial joint penetration. That is, they were not intended to be complete joint penetration welds. Then drop down to the next paragraph and highlight that, put a bullet by it, and it says, it should be noted that previously the condition now correctly referred to as incomplete joint penetration has been called by several non-standard terms. Some of these were inadequate penetration, lack of penetration, and those would be abbreviated IP and LP, and those are terms that they use in the 1104 code. For groove welds, the correct term is incomplete joint penetration and should be used instead of the other terms. Here we're back to that picture again. And now this then would be considered incomplete joint penetration unless, of course, it was designed that way by the engineer. And over here, you can see it's very distinguishable on an X-ray. It just creates a really straight line. Staying on page 910, highlight the last paragraph. It says, incomplete joint penetration can be caused by the same conditions which result in incomplete fusion. That is improper technique, and I've underlined that again. Improper technique, improper joint configuration, or excessive contamination. Any of those things could lead to incomplete joint penetration. Inclusions. Entrapped foreign solid materials such as slag, flux, tungsten, or oxides. On page 911, I've highlighted the entire column under inclusions, and it says, put a bullet by where it says the definition of inclusion is entrapped foreign solid materials such as slag, flux, tungsten, or oxide. Thus, the term inclusion can include both metallic and non-metallic categories. Slag inclusions, as the name implies, are regions within the weld cross-section or at the weld surface where the molten flux used to protect the molten metal is mechanically trapped within the solidified metal. Go ahead and read the remainder of that. Next paragraph, like incomplete fusion, slag inclusions can occur between the weld and base metal or between individual weld beads. In fact, slag inclusions are often associated with incomplete fusion. Drop down a little bit. Underline where it says often the improper manipulation of the electrode or incorrect welding parameters could result in undesirable weld profiles, which could then hinder cleaning of the slag between passes. Subsequent welding would then cover the trapped slag to produce slag inclusions. So if a person's welding and they're not using a proper amperage or something like that, they're not manipulating the electrode properly, they could get a bad bead profile and trap some slag underneath that and not realize it's there, or not clean it properly and then weld over top of it and they have slag inclusions. Probably the most common cause I have seen is sidewall or groove face slag entrapment, where they'll be putting the weld in and they'll undercut the groove face, and when they undercut it, they'll often trap slag in that undercut, and then they weld right over that. So it's improper cleaning. They should have ground it out and they didn't do it. Bullet by where it says figure 920 has the appearance of slag inclusions, but is actually penetration faults at the starts and stop areas. Oops, don't know if you guys have this one. Here we go. This is an x-ray. This is on the next page. This is on page 913, the very top radiograph. And these are, if you've gone through my classes, I've talked to you about these. These are toenails. It's simply where your root pass didn't blend in and you've left these little voids. So these are penetration faults. This picture is on page 912. Surface slag inclusions. You can see we've got some slag trapped back in here, slag along this upper edge, slag trapped under here. This would be, we've got some undercut here, some overlap, and there's slag trapped back in the overlap. So highlight directly under that picture, and then put a bullet by the next paragraph where it reads tungsten inclusions. It says tungsten inclusions are almost always associated with the gas tungsten arc welding process, which uses a tungsten electrode to produce an arc. And let's see. Well, before I get to that, here's another slide. This is elongated slag inclusions. Now you can see they differ a little bit from the fusion one. If you look at page 910, figure 9.15, and compare that to figure 9.21, they're similar, but you can see that the line on the slag inclusion is a lot more solid. It's not as intermittent as the lack of fusion one on page 910. So it's sometimes difficult to tell the difference between elongated slag inclusions and incomplete fusion, but you want to look for the more complete line, the more solid line. And here we're finally getting to an X-ray of tungsten inclusion. Now, because the tungsten is so dense, it blocks most of the X-rays from reaching the film. Therefore, their image shows up as a light spot, a white spot, and they're very easy to pick out. So this would be what it would look like on an X-ray. Let's see. Before we move on, go ahead and highlight all of the first column on page 912. In the second column, right beneath figure 9.18, between that figure and the blue box, go ahead and highlight all of that, and then read the material in that blue box. And then right beneath the blue box, let's highlight it from where it says tungsten inclusions are seldom found on the surface of the weld, unless the welding inspector has the opportunity to look at an intermediate pass after a piece of tungsten has been deposited. The primary way in which tungsten inclusions are revealed is through radiography. So that's the main way we're going to get them. It's not really simple to do the to locate them visually unless you're actually watching the welder as he's welding. And the other type of tungsten inclusion besides the one we saw on the film is the shed that I talked about earlier, where the outer layer from you're using too high an amperage, and the outer layer becomes loose, and it'll just shed and be shot into the weld, and that'll kind of look like pepper. It'll be peppered all through there, all through the weld. Okay, let's turn the page to 914. And porosity. Cavity-type discontinuities formed by gas entrapped during weld metal solidification. Okay, on page 914, I've highlighted the first three paragraphs, and there's a number of bullets here. It says, AWS A 3.0 defines porosity as a cavity-type discontinuity formed by gas entrapment during solidification. Therefore, we can think of porosity as being voids or gas pockets within the solidified weld metal. Due to its characteristically spherical shape, porosity is normally considered to be the least detrimental discontinuity. Bullet, underline it, least detrimental discontinuity. However, in cases where a weld must form some pressure boundary to contain a gas or liquid, porosity may then be considered to be more damaging. This is due to the possibility of porosity providing a leak path. I discussed that earlier. Particularly with cluster porosity, it could reduce the wall thickness and allow that metal, the liquid or whatever it's containing to precipitate or to get out of there. Next paragraph is a bullet. It says, like cracking, there are several different names given to the specific types of porosity. They refer in general to the relative location or the specific shape of the individual porosity pockets. Therefore, such names as, and these were mentioned in the film, so underline them, uniformly scattered porosity, cluster porosity, linear porosity, and piping porosity are used to better define the occurrence of porosity. A single cavity is also referred to as porosity or a cavity. Then it goes on to tell us about these. It says uniformly scattered porosity refers to numerous cavities which occur throughout the weld in no particular pattern. Let's see. I have something on that. Here we go. This would be scattered porosity, and you have this in your book, uniformly scattered porosity. And you can see it's here, 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 here. For me to look at that, I kind of think that would be dual shield that they used, and probably to get that result, they just didn't turn the gas on very high, and so they could go ahead and produce a weld like that for inspection purposes. Then we have cluster porosity and linear porosity. This is linear porosity with a connecting crack. So this would be a longitudinal crack, and you can see the porosity is in a straight line, and in fact the porosity is what caused the crack to form. This is isolated surface porosity. This is figure 9.25 in your textbook. And let's see. Elongated surface porosity. This is the last slide. Directly opposite from that picture, highlight and put a bullet by that paragraph where it reads, there are some types of porosity where the individual gas pockets are not spherical but are elongated. That's a bullet. Figure 9.26 is an example of elongated porosity occurring at the weld surface. This is often referred to as wormhole porosity. That's another bullet. Drop down to the bottom of that paragraph, that bottom of that column, highlight it, put a bullet by it. Another form of elongated porosity is piping porosity. Piping type porosity usually represents the most detrimental condition if liquid or gas containment is the primary function of the weld, because it represents a more significant leak path possibility. Porosity is normally caused by the presence of contaminants or moisture in the weld zone, which decompose due to the welding heat and form gases. So here's a picture, an x-ray, of scattered porosity, and you can see it's a little bit here, a little bit here, a little bit here, some more back down in here. So it's scattered, it's stretched out. Now, as mentioned earlier, most codes will allow some porosity, and that brings us to the reason for staggering your starts and stops. If we're welding if I'm welding a piece of pipe and I start bottom dead center and I weld up this way, and then I start bottom dead center and I weld up this way, and now I grind it out and I start my next bead and I come up here and that's all the farther I got. Well, I finish that off and then I weld it up here and I stop and I start again. And all my starts and stops are essentially in the same place. And if I'm just picking up one or two little bits of porosity on each one of those, that may put enough in one small area that I would be out of code. If, however, I'm staggering them and I've got one here and one here, maybe one here, one here, now I've stretched them out over a larger area. I still have the same amount of porosity, but I've quadrupled the area that they're put on by stretching them out like that. Now that may be within code. That might be acceptable to code. This might not be acceptable to code. So you always want to, when you're welding, you always want to stagger your starts and stops. Okay. Here's an X-ray of cluster porosity. This is on page 9.15. Cluster porosity is not allowed. Nothing that I've ever worked with allows cluster porosity. A lot of times cluster porosity will appear on a bend test, on a face bend test. You can spiffy it up and grind it down and smooth it out, and it looks fine until you throw it in the bend tester, and as soon as you stress it, you'll see the porosity pop out like that. And this is an X-ray. I don't know if you have this. Yes, you do. On the next page, 916, top of the page, you have this same picture, a radiograph of linear porosity. This is running right down the center of the weld. And that brings us to undercut. Undercut. Highlight it, bullet, define it. This is real similar. A groove melted into the base metal adjacent to the weld toe or weld root and left unfilled by weld metal. That's almost identical to the definition we had earlier. So highlight that paragraph. Know that definition. Here, this is in your book. Here we see undercut here on a fillet weld. Undercut on the back side of this weld here. Now, if this occurred in piping, this would be an automatic failure. On piping, there is no internal undercut allowed, so that would be a bust out right there. Undercut on the surface. Some amount of surface undercuts allowed by most codes. You have this picture in your textbook. The way we examine, the way we look for undercut, I think in your book it's turned upside down. The way we look for undercut is to take a flashlight and we'll hold it down along the edge and we'll shine the flashlight, and then it will cause the undercut to cast a shadow. A good rule of thumb is if you can hook your fingernail on it, it's too much. On page 916, second column, highlight the two paragraphs on undercut where it begins. Undercut is normally the result of improper welding technique. Start there and highlight it on down to the end of that topic. Then go ahead and go to underfill. Bullet, highlight it. Underfill, like undercut, is a surface discontinuity which results in a loss of material cross-section. However, underfill occurs in the weld metal of a groove weld, whereas undercut is found in the base metal adjacent, in the base metal adjacent to the weld. Now, there's two types. This is called underfill. So if we have a joint like this, and we don't fill it up all the way, that's called underfill. And you can measure that and see it and so forth. And really, the welder just didn't fill it up enough. If you get it here on this side, that is often referred to as suckback. But that's an improper name, and it's more properly called underfill. If I were inspecting and writing a report, I would probably put it in parentheses, suckback, or insufficient penetration, something to that effect. But the proper name, again, would be underfill on the root side, words to that effect. Now, if we're talking about a fillet weld, you have to bear in mind that when they talk about underfill, that's only relevant to groove welds. If you have underfill on a fillet weld, that's not called underfilled, that is called convexity. Pardon me, concavity. Let me get this right. Concavity. So, concavity on a fillet weld, underfill on a groove weld. So, keep those two terms in mind. Then, let's see, go to page 917. You have these pictures. These are pictures of underfill on groove welds. And right beneath that picture, highlight it and put a bullet where it says, like undercut, underfill can occur at both the face and root surfaces of the weld. Underfill at the weld root of pipe welds is sometimes referred to as internal concavity or the slang term suckback. It can be caused by excessive heating and melting of the root pass during deposition of the second pass. Then over the next column, highlight where it says the primary cause of underfill is the technique employed by the welder. Excessive travel speeds do not allow sufficient filler metal to be melted and deposited to fill the weld zone to the level of the base metal surface. Now, as we're going through these, every one of these topics is going to give you a reason why it happened. And note the reasons why things happen. Why do they occur? Because as the inspector, you're going to have to be able to identify what caused it. And sometimes it'll be welding metallurgy, but most times it will be improper technique employed by the welder, which points out the fact that we have to test. We have to test. And as I've mentioned before, my success rate on welder certification testing is about 17%. 17 out of 100 people will pass a test the first time they do it because their skills erode, their skills lapse if they don't do it all the time. So we have to keep testing. Overlap. Bullet highlight. I actually underlined where it says overlap is described as the protrusion of weld metal beyond the weld toe or weld root. And I underlined that in my text. Here we're back to these slides again. Same slides that showed our undercut. Well, now they're pointing out overlap. And so you can see here the overlap on this fillet weld. You can see it's reduced the size of that fillet weld. And this is excess metal that's just flowed out onto the parent metal. Again, this kind of a discontinuity where you have weld metal running down on the inside of pipe, that would be an automatic failure. You cannot allow that because why? It's an internal stress riser. Here you have overlap on the outside of a pipe, and that would be a discontinuity. If it exceeded code standards, it would not be acceptable. Here we have these are on page 918. We have some pictures of overlap. Overlap here, trap slag, undercut up in here. That's just a pretty bad weld. Overlap here on a groove weld. Looks like they might have welded this from the top down in the horizontal position, deliberately making this overlap like so that we could see it. On page 918, put a bullet by the paragraph which reads, overlap is considered to be a significant discontinuity since it can result in a sharp notch at the surface of the weldment. So a significant discontinuity, it's a stress riser. Highlight the remainder of that topic. Go to the next column, convexity. It reads, this particular weld discontinuity applies only to fillet welds. Convexity refers to the amount of weld metal buildup on the face of the fillet weld beyond what would be considered flush. By definition, and I underline this part, it is the maximum distance from the face of a convex fillet weld perpendicular to a line joining the weld toes. So, let's see. Let's get past that. This is your definition, the maximum distance from the face of a convex fillet weld perpendicular to a line joining the toes. I don't know if I have a slide of that. Yes, I do. Good. So here would be the face. And here's a toe, and here's a toe. So remember we had the theoretical throat, the effective throat, and the actual throat. So anyway, this material right here is excess. That's unnecessary. And if we get too much of that, then that will create a stress riser. The American Welding Society places limits on the maximum amount of convexity that is allowed. I highlighted the entire column here, in fact the entire topic under convexity. Read it all, but go to the middle of that second paragraph and highlight it where it says, the real problem created by the existence of excess convexity is that the resulting fillet weld profile now has sharp notches present at the weld toes. These notches can produce stress risers which could weaken the structure, especially when the structure is loaded to fatigue. So if we look at this, let me see if I can dry this off. So if we look at an excessively convex weld like this, well, this is all excess, and you can see the angle that is created here. Well, vibratory stresses are not going to be able to pass through that very well. They're going to focus right here. They're going to concentrate at the toes. And so that's a stress riser, and that's why they are so detrimental. Because it'll cause that stress riser, the stresses will be concentrated there, and it could lead to failure. There's a nice picture of it. Your figure 9, I don't have that slide, but there's a nice picture of it on the bottom of page 918 where they're showing an excessively convex weld, and you can see how it's almost square. The weld nugget that they're showing us here is almost square, and that just results in too high stresses. Weld reinforcement, next page, bullet, highlight. Weld reinforcement is similar to convexity except that it describes a condition which can only be present in a groove weld. So they're making the distinction between groove welds and fillet welds. For excess convexity, excess convexity, concavity, pardon me, and then over-welding or excessive weld reinforcement. Put a bullet by where it says weld reinforcement is described as that weld metal in excess of the amount required to fill a joint. Very simple definition. Weld metal in excess of the quantity required to fill a joint. And here's a nice picture of it. You've got this in your book. They have excess face reinforcement and excess root reinforcement. And remember, they put limits on this, typically 1/16 to 1/8 of an inch on root and face reinforcement. Face reinforcement from both sides. If it's been welded from both sides, then you have to call it face reinforcement from both sides. It's no longer considered a root reinforcement because it's been welded from both sides. Looking at page 919, drop down to the last paragraph in the first column, highlight that, put a bullet by it. It says, like convexity, the problem associated with excessive reinforcement lies with the sharp notches that may be created at each weld toe instead of the fact that there is more weld metal present than is necessary. So if you have too much, just like we had here, you can turn this baby on its side. And if we've got too much here, again, we're changing this angle, and we're concentrating stresses right here at the toes because this is too much of an angle. So we have to fix that in some manner, and your book describes this on the next page. They show how they blended it in, ground it, blended it in, so that we have a smooth transition, and we've removed those stress risers. If you look at the next page, figure 9.40, you'll find this, and here they're showing excessive weld reinforcement. And over here, if you see that and you tell a welder, hey, fix that, that's too much, a welder is typically going to grab a grinder and knock off the head of it. Well, that still hasn't changed the angle that we have here. To fix this, you've got to change that angle. So our last picture down here shows us how it's properly been changed, how they've ground into it a little bit and they've transitioned it a little more smoothly. So now that stress riser has been removed. So if you have to encounter something like this, make sure that whoever's doing the repair doesn't just knock off the top of it, because that does nothing to remove that stress riser. Okay, arc strikes. A discontinuity resulting from an arc consisting of any localized remelted metal, heat affected metal, or change in the surface profile of any metal object. That's a pretty long-winded explanation. but that's what they call it. Everybody pretty much knows what an arc strike is. Reading under that topic, it says the presence of an arc strike can be a very detrimental base metal discontinuity, especially on the low alloy high strength steels. Arc strikes result when the arc is initiated on the base metal surface away from the weld joint, either intentionally or accidentally. When this occurs, there is a localized area of the base metal surface which is melted and then rapidly cooled due to the massive heat sink created by the surrounding base metal. On certain materials, especially high-strength steels, this can produce a localized heat-affected zone which may contain martensite. Just think back to Module 8 where I drew all that up on the board, and we saw how if you quenched it from a high temperature, you would create formation of martensite. And what's wrong with martensite? Well, it's high strength, very low ductility, and it'll crack. And you have this picture in your book. It's the top of the next column, and you can see radiating out from this arc strike are these little micro fissures. Now this is probably a high carbon steel, high strength, high carbon steel, but it illustrates what can happen with arc strikes. Arc strikes are not necessary. If you have a welder, a craftsperson that's consistently doing this, after about the second time, I'd pull his papers. There's no reason for that, especially if you're working on important, critical stuff. A person should be good enough that they don't do that. If not, they're either lazy or incompetent. So right under this picture, highlight it, and we'll put a bullet here. It says, arc strikes are normally caused by improper welding techniques. Welders should be informed of the potential damage caused by arc strikes. Most people don't know that it can create cracks. They just don't know, and they're lazy. So tell them once, if they keep doing it, that's it. Due to the potential damage they represent, arc strikes should never be permitted. And underline, put a bullet by this, the welder should not be performing production welding if he or she insists on initiating the welding arc outside the weld joint. So just don't let it slide. Next topic, spatter. Metal particles expelled during fusion welding that do not form part of the weld. So find that and just highlight it under that topic. Read about that. Then over on page 921, highlight about the first half of that paragraph where it reads, in terms of criticality, spatter may not be a great concern in many applications. However, large globules of spatter may have sufficient heat to cause a localized heat-affected zone on the base metal surface similar to the effect of an arc strike. Also, the presence of spatter on the base metal surface could provide a local stress riser which could cause problems during service. You have this picture in your textbook, and again, we're probably dealing with a high-strength, high-carbon steel, but you've got a red-hot globule of spatter that hit on there, and it caused a crack, and you can see that. So spatter, again, should be kept to a minimum. If you're getting excessive spatter, there's probably something wrong. You might have severe magnetic arc flow, or the person may be long arcing, so there's a problem with their technique, or they may be running too high a current. There's something causing excessive spatter. Now, a little bit of spatter is normal, and you're going to get more spatter with some processes than with other processes. But if it looks like you've got excessive spatter, then you need to investigate why you have excessive spatter. Staying on page 921, go to the next column and highlight the last paragraph where it talks about spatter. It says, spatter can result from the use of high welding currents, which can cause excessive turbulence in the weld zone. Some welding processes are considered to be characteristic to produce more amounts of spatter than others. For example, MIG tends to produce more spatter using the spray arc, blah, 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 and so on and so forth. So read that column and understand some of the causes of that. And that brings us to a lamination. And a lamination is a discontinuity with separation or weakness aligned parallel to the worked surface of a metal. I like my explanation better. Think of it as being a sandwich. They call them stringers. You get stringers in the layer, in the matrix, and when the material is rolled out, they elongate, and it's an interruption of the base metal, and it's done at the foundry. So put a bullet by that and highlight that on page 921. Flipping the page, go ahead and highlight it down all the way to the first paragraph where it says B1.10 refers to delamination as the separation of a lamination under stress. You have this picture in your book. Cracking and delamination due to a lamination. Well, we had the lamination over here in the base metal, and then we made a weld, and whenever the shrinkage forces of the weld came into play, it pulled the lamination apart, causing a delamination, and then the crack continued on into the weldment itself. So that is a lamination turning into a delamination. So highlight that. Then drop down to the third paragraph and highlight that, where it says, if a lamination is present on the surface of a weld preparation, it can cause further problems during welding. In such a case, weld metal cracks can propagate from the lamination due to a concentration of stress. And an example of this is what we're seeing in 9.44. Another problem related to the presence of laminations open to the groove face is that they are prime sites for the accumulation of hydrogen. We talked about hydrogen before, how they can form molecules and cause additional cracking. Drop down to the last sentence in that first column. Highlight that to the end of the topic where it says the best method for the discovery of laminations other than visual inspection is the use of ultrasonic testing. And then radiography will not reveal laminations because there is no change in the radiographic density of the metal even if it is laminated. So read about that. And then we come to a laminar tear. Well, delamination, first of all, is the separation of a lamination under stress. And I happen to have a delamination. I'm sure you cannot see it, but in this little fillet weld, we had a little weld here, and there was a lamination right centered up underneath this perpendicular piece here, and it's right there. If I PT'd this, it would bleed out, and you'd be able to see it a little bit better. But it was a lamination, came from the mill, this weld was made, and that shrinkage stress pulled that metal and it opened it up, so we now have a delamination. It's hard to see, but it's just about centered up here and here. I use this in my inspection class, and I pass it around with a magnifying glass, and I let all the students look at it, and I know it's probably impossible for you to see it sitting out there, but nevertheless, that is a delamination. Okay, a lamellar tear. Highlight it, bullet. It says a subsurface terrace and step-like separation in the base metal, parallel to the surface, caused by tensile stresses in the through thickness direction. So highlight all of that, all of that column, and over on the next page, we have some pictures. Let's see. I don't think my pictures quite mimic yours, but they're similar. Here you can see the weld running down, and here in the base metal, look at the tear right here, and it's just right adjacent to the weld. Ditto over here. And again, this tear was caused by the shrinkage forces of the weldment. It tore the base metal. And as I mentioned before, it's usually associated with cheap steels. Sometimes you get a batch of steel that might have come in from someplace overseas where they just wanted to crank it out and sell it cheap, and they didn't bother to refine it properly enough, or it slipped past the inspectors. It could have been unintentional and slipped past the inspectors. And it just causes problems, and of course there's no doubt that that would lead to weld failure. So read about that. Let's see. Over on page 923, in the second column, highlight the last paragraph where it reads, for the onset of lamellar tearing, three conditions must exist simultaneously. They are stress in the through thickness direction, susceptible joint configuration, and material having a high inclusion content, meaning there would be a lot of stringers in those things. And of course the through section, when we talked about the X, Y, and Z, Z was the through section direction, and that's what our picture showed there. And figure 9.45 shows the tearing in the through thickness section area. That brings us to seams and laps. Definition, underline it, highlight it. Longitudinal base metal surface discontinuities found in wrought products. Seams and laps are additional base metal discontinuities related to the steel making process. They differ from laminations in that they are open to the rolled surface of the metal instead of the edge. So again, if you remember going back to one of our previous lessons, we had the X, Y, and Z directions. So this would be our rolled surface. A lamination might appear out here, but on seams and laps, they're more likely to appear here on the top. If cross-sectioned, they may run parallel to the rolled surface for some distance and then tail off toward the surface. Seams are described as straight-line longitudinal crevices or openings that may appear on the surface of steel. Seams are primarily caused by imperfections in the steel ingot, by improper handling after pouring, or by variations in heating and rolling practice. Laps are the result of overfilling in the rolling mill passes that cause fins or projections which turn down as the material rolls through succeeding strands. So what's happening is, as they, hang on one second. If this is a piece of steel that they're rolling out and they overfill it and they're trying to pull it, what happens is it gets pushed back here and it starts to run down the sides, and it goes through those and it gets smashed into the side. So it's just laying on there. It's just adhering on there. And that's what's going to happen with your laps. Let's see. Here we have, I believe you have this picture on the next page. Yes. Here we have some slides. This one you can see right here. We have deep seams on surface of a semi-rolled finished product. Well, it's semi-rolled, and they're seeing this, and their quality control people would catch this, and they'd say, hey, let's get it out of here, put it back in, let's melt it down again and try over. Here's another one. Now this stuff, you can see this, it almost looks like mill scale, where it's just kind of standing on there, and if it were truly mill scale, you could take it and flake it off. And you could just run your hand over it or run your glove over it, and you would see that stuff just pop off of there. But you got to be careful that it doesn't run on down into the metal itself. And then we have this one, this final one, and this is a lap on the surface of a rolled steel billet. So again, any of these things that are caught at the foundry, they should, pull them out of production and drop them back in the furnace again and melt it down and start all over with them. So you got some nice pictures of what can happen there. And then that brings us to dimensional problems. So what are they? Size irregularities, shape imperfections, and distortion. So under dimensional, highlight that entire section on 923, flip the page, and then you can stop there where it says check by welding inspector. Just read about that. And then we have discontinuities in laser and electron beam. I'm not going to worry too much about that. There's I don't believe you're going to have any questions at all concerning discontinuities in laser and electron beam. But beam deflection is one, porosity, shrinkage voids, hot cracks, lack of fusion is another one. It's not really going to be important to our purposes, so I'm not going to give you any questions on it. But it does bring to mind one thing that happened one time, where it talks about missed joint in your book. One example of a missed joint is, I attended a seminar some time ago, and they talked about weld failure. This guy was an expert witness, really a sharp guy, named Ken Coriel, from Ohio, welding engineer, and lots of degrees and stuff. And he was called in as an expert witness on a case where they had a weld, and it was like that. And they made the weld in there using the TIG process. And what they did was they ran a machine up the inside of this material, and it was welding from this side. They ran another machine on top, welding from this side. So they made a weld here from both sides using automatic TIG, and I'm almost certain it was TIG, and they ran it down 20-foot lengths or whatever and sealed it off. And then when this material was done, they pressure tested it. They capped both ends and they pumped it up with with working pressure plus 10% or whatever, and it held just fine. So great, pass test, ship it out. Well, the problem was misalignment. What happened was as this one was coming down here, it was creating a weld like this, and as this one was going in here, it created a weld like this. And the joint, well, it was a square butt joint that ran down like this. And so you can see that the top one caught a little bit here and sealed it. The bottom one caught a little bit here and sealed it, but this whole big section in here, right in there, no weld metal. So it was strong enough to withstand 110% of the working pressure during the pressure test, but once it got put into service, it failed. And he proved this in court, and what they should have done was, as we've talked about before, they probably should have done non-destructive testing through UT. UT would have caught that in a heartbeat, and of course they would have written that up like in their inspection symbol, like so, UT 4 places, 12 inches, la-di-da, and they would have written that up, and they would have spot checked that, and they would have found out that they were having problems through misalignment. So that was just a lapse in quality control. But that's the kind of stuff that can happen out there in the field. Okay, summary. Go ahead and flip the next page. Let's see. Let's go to key terms and definitions. Do some little bit of highlighting here, not a whole lot, but these will help you to focus your studies. Arc strike, highlight that. Crack, highlight that. Crater crack, defect, delamination. Next column, start with discontinuity, inclusion, incomplete fusion, incomplete joint penetration, lamellar tear, lamination, overlap, porosity. Next page, seam / lap, slag inclusion, spatter, stress risers, stringer. Now let me read that. In metallurgy, an elongated oxide or non-metallic inclusion within the metal that can cause your laminations. Over on the next page, tungsten inclusion, undercut, underfill, and weld reinforcement. So read that chapter. Take note of where I've mentioned you need to highlight and put bullets. Watch the films. And then I have a practice quiz, which should be included with this work packet. And let's see, it runs about 20 questions, it looks like. And that will help to prepare you. Okay. Contact me.